Nice. Okay. So perfect. Okay. Let's do that. All right. Dave, go ahead.
Sorry.
Yeah.
Battery-powered electronics experience fluctuations in input voltage due to battery discharge and variations in load, and this can negatively affect the system performance. So to solve this problem, we are offering a DC-DC converter, and specifically buck boost because it can increase and decrease the input voltage. This flexibility makes it ideal. In this project, we focus on the design and simulation of an inverting buck boost converter, and we simulate it with two different control methods. So first, to look at the controllers, here we have a knob and two sliders to control the gain. And our efficiency goal is to have it above 85% with low ripple, lower than 5%, and fast transient recovery. Uh, and here to look at the circuit topology, we can see that the input voltage source provides energy to the converter, in our case, which is the battery supply. Next is the inductor, which temporarily stores energy in its magnetic field. The current flows through it and releases that energy to the output when the switch is turned off. The MOSFET switch is the switch element. It turns on and off rapidly, controls the inductor, it stores energy, and then transfers it to the output. The diode here
Oh, sorry.
the diode here ensures current flows unidirectional. So when the switch is turned off, the diode becomes forward bias and allows the inductor to deliver its stored energy. And when it's reversed biased, when the switch is turned on. The capacitor filters the voltage and reduces ripple to make it smoother and have a more stable output. And of course, the load resistor represents the device that consumes the power from the converter. As we can see in the next slide, the duty ratio. Yeah, the duty ratio represents the fraction of time the switch will remain on during one switching period. And we can compute it with the equation we have here, the output voltage over the output voltage minus the input voltage. This is the duty ratio if we solved for D from the previous transfer function, and we have a negative V out because obviously this is a inverting converter. And the converter is designed to operate in continuous conduction mode, which means the current never drops to zero, as we can see here. The current increases and then decreases without touching zero, and this is important to guarantee system stability and allow more predictable control. The first method is the standard PI controller.
Uh, so I'll discuss the inductor sizing first, and then we will discuss the control method, right? So
Yes, go
for
ahead.
for the inductor sizing, we as Saif mentioned, we need to stay in continuous conduction mode, which means that our current through the inductor should never hit zero. We did this by first off, we solve for the equation of inductance from by isolating the inductor value from voltage across an inductor. If you do this analysis when the switch is on, VL is equal to Vin, and then it's a small integral which the dt is the duty cycle times the period, which is the divided by the frequency, and then delta I is the current ripple. We chose our current ripple to be twice the minimum possible current. So if you think, if let's say our minimum current is this 0.04 here, then if our ripple above and below, it never hits zero, this ripple is constant. So as if this current goes up, this ripple will stay constant and we won't hit zero. So as long as we don't hit zero current, 0 amps, at lowest possible current in the inductor, we will always be guaranteed to operate in CCM. As for the capacitor, we chose a maximum voltage ripple of 5% in worst case scenario. Again, by solving for the capacitance from the equation of current during a capacitor, we can isolate for C, and by subbing in 0.05 V out for the delta V, we can replace the I out over V out by the resistance, and then we can calculate the maximum minimally required capacitance, which is the capacitance required at worst case scenario, which happens at the highest duty cycle and the lowest resistance load. And we solve for that to be 66.7 microfarads. We can see here the equations that we used. So this is the equation which we solve for the current through the inductor. We did some clever substitutions because we wanted everything to be a function of D and R, because V in is constant. So this gives us a two input function for all of our components. So for calculating the L, we had to calculate the minimum possible current in an inductor, and that happens at D min R max. And using our equation derived from the slide below, we get 0.0375 amps. We want our ripple to be twice that, so that this minimum current happens in the middle of the ripple. So our delta I is 2 times I min, and subbing in our D and R values from the I min equation, we get our inductance of 2.2 millihenry. And then same thing for capacitance. We solve for the capacitance, and then, as I said, subbing in 0.05 V out for delta V, I over V is just 1 over R, and D max over, and it's D max R min gives us our capacitance value. Okay, and then back to Saif for control methodologies.
The first control method is a standard PI controller. As we can see in the next, here the first controller, as we can see, measures the difference between the reference voltage and the output voltage, and then adjusts the duty cycle to minimize that error. The difference between the voltages is then multiplied with the gain and fed to the PI controller, which is then fed as an input to find the duty cycle to regulate the circuit. And the difference here in the cascaded PI control, which is our second control method, in this approach, 2 control loops are used. The outer voltage loop, the difference between the reference voltage and the output voltage is when that difference is fed to the PI controller, it can determine the desired inductor current based on that voltage error, while the inner current loop adjusts the duty cycle by comparing the desired current that was computed. It compares that with the actual inductor current that is measured across the inductor. So here it is cascaded because it is a 2-loop approach, 1 loop and then the other.
Here's some simulations for that, and we ran both control methods at our minimum design load and our maximum design load. And then here's some tuning mechanisms that we use. So we use the Ziegler-Nichols method for tuning, which essentially required us to find the ultimate gain. The ultimate gain is the p-value, which causes the system to oscillate indefinitely and never settle, and it's just before instability. And then we found the period of that oscillation, and using that we were able to calculate our Kp and Ki values for our PI controller. And we see here that it resolved our steady state error while maintaining the voltage ripple and CCM mode. And we see also that the voltage ripple, as we calculated earlier, happens at the lower resistance values, and then the more we increase the load, we have less voltage ripple. Here's some simulations for our cascaded controller, which, as Saif discussed, and then we tuned that using essentially the inner loop. We tuned because the current through the inductor allows us to treat the inductor as an integrator. So we tuned that loop first, and then we tuned the outer voltage loop because voltage in a capacitor is also a simple integrator transfer function. So here we see our formulas. So for a PI controller using the Ziegler method, once we get our Ku and Pu, we can use these formulas and get our values. And then as we said, the inductor gain is an integrator. Voltage in a capacitor is also an integrator. And then we used just simple tuning formulas, which by calculating the inner frequency, the outer frequency, and essentially our inner frequency is 1/10 of our switching frequency, and our outer frequency is 1/10 of our inner frequency. Using these two equations, we were able to calculate our Kp values, and then using these two equations, we're able to calculate our Ki values. This is actually a very quick and effective tuning strategy for us. Finally, to prevent we didn't want the voltages to shoot up to unexpected ranges. If you look at the duty cycle or the voltage out equation, the transfer function, if you have a duty cycle of 1, you're going to have an infinite outage voltage. So we saturated our duty cycle output to 0.25 and 0.75, which is essentially a 20% increase and decrease from our maximum ideal duty cycle calculated value. So we can show this in Simulink quickly. So at first, we can run the PI controller in Simulink, and we're running it at 10 ohms and with the tuning that we discussed. And we can see here, and we can see how it handles the transitions. And perfect. So we can see that our voltage ripple is less than 1 volt across that 20, and then it's even less at lower voltages and will be less at higher resistance. This is exactly what we expected. And we see unfortunate voltage overshoots when transitioning from, I guess it would be low voltage to high voltage, but in our case, because it's inverted. And then we can do a simulation for the cascaded controller, which we see works a little bit better, especially at low load. So it doesn't have the overshoot, and you can have the transitions. And yeah. Perfect. So we see that this has no overshoot both ways, but it does have this overshoot when transitioning from a lower voltage to a higher voltage. This is a difficult problem to solve, but it can be reduced at higher voltages or by adjusting the gain. We can also run a comparison between both, and then we will run a comparison at a higher load as well. Here, and then we can look at transition. So comparing both control systems, it depends. It depends on the design specification and use, but we feel like they're pretty comparable in terms of settling time. The cascaded has a lower overshoot, but at such a low load, it's you can use either one, but we feel that the cascaded shines when we increase the load. So if we increase our resistance to the maximum rated value of 200 ohms, we have to retune our controller. So we have a tuner gain slider for each controller, and what this does is allows us to quickly retune the PI system while maintaining the ratio between the I and P values. So if we run this, we see perfect. So when we do this analysis, if we did not reduce our gain for the PI, we would have significant voltage ripples. Reducing the gain gets rid of the voltage ripples, but causes aggressive overshoot, and it significantly increases the settling time. For the PI, we have some instability, but once we adjust the gain, we end up with a pretty ideal system. We see there's no overshoot in the transitions, and the settling time is still very good. And even it struggles at the lower voltage, but even then, it still has minimal overshoot, nothing aggressive, and it has much better settling time than just the PI controller. So that's our simulations, and I will go back to Alan for the comparisons.
Okay, so in comparison, our first control method was traditional PI loop using Ziegler-Nichols tuning. We found an ultimate gain of 1.67 and a period of 4.84 milliseconds. And based on our Simulink, the PI control suffered moderate overshoot and slower settling time as compared to the cascaded controller, which is a more faster and cleaner response under the load of 10 ohms. So in summary, our recommendation is to use the cascaded control for variable loads, and inductor saturation is the primary failure risk as our lessons learned. Duty cycle saturation from 0.25 to 0.75 is our critical for safety. Conclusion. So our conclusion is our design successfully validated by Simulink, and we use the proper tuning methods like Ziegler-Nichols and frequency domain. And final converter provides stable negative rail for battery resistance.
Okay.
That's it.
Yeah.
Thank you.
Thank you. Do you want to just check the time on the recording? I hope we didn't go over 10 minutes.
Where is the recording? Inscription. Stop.